the tech lead for the Hadoop platform team at LinkedIn. And today the topic is the past, present, and future of Hadoop at LinkedIn. And I want to start by apologizing for the title of this talk, which I now realize is something of a bad cliche, and to thank everyone for still taking a chance on this talk and attending. At the same time, though, I like the history element of it. I've been involved in Hadoop since 2009, and I've seen the platform and the ecosystem change a lot. I think in some predictable ways as well as unpredictable ways. And when I joined LinkedIn, one thing I did was investigate how Hadoop started there, and I think it provides sort of some interesting insights. So the story really begins back in 2006 when LinkedIn built a new feature called People You May Know. The original implementation ran on Oracle, and fundamentally what this feature was all about was connecting people who may know each other, suggesting connections, and building and tightening the graph. Fundamentally, PymK is about triangle closing. The idea is that you have users, Dave, Mary, and Steve. Dave knows Mary, Mary knows Steve. It's a pretty good assumption to make that Dave may know Steve, and we suggest that connection. You expand this process out, and pretty quickly, you have a more connected graph. PymK was a huge success. It's widely viewed as one of the features that drove the growth of LinkedIn, and it quickly became, in effect, a victim of its own success when what had originally taken, let's say, 6 weeks to do a complete run through all of the members on the site was now taking 6 months. And when you're running a process that depends on data that's up to 6 months old, you may be suggesting connections to people who no longer exist on the site, to people who are no longer connected, and things quickly got embarrassing. So this was identified as a top-level priority to figure out a way how to scale this feature. At about the same time, Yahoo had open-sourced Hadoop, and some engineers at LinkedIn heard about this and thought, well, you know, this could possibly be a way of improving PymK. I joined LinkedIn about 2.5 years ago, and one of the things I did after joining was to go look through Jira and try to find the first reference there to Hadoop, and this is what I found. And you see some sort of interesting things. People are talking about running Hadoop on Sun hardware. There were other comments in this ticket about what the right replication factor should be, and people seem to think it was 2. And I should add that the people who were participating in this project were really smart. But I think this is indicative of the fact that no one at the time really knew how to run Hadoop outside of Yahoo. There were no books available, no training courses available. Not many people were even blogging about it. So it took quite a bit of effort, I think, to get this project up and running. And it's remarkable that it was as big a success as it was. So by 2009, PymK was running on Hadoop. LinkedIn had a 20-node cluster running a fairly primitive, older version of Hadoop. And what had taken 6 months was now being done in 3 days. So I think, and we've seen this pattern in a lot of other companies that start using Hadoop, it starts basically with one critical project, usually with a group of engineers who just cobble hardware together, and pretty soon the success of it sort of snowballs from there. So that brings us to the present at LinkedIn. So in terms of sort of Hadoop by the numbers, we've grown from 1 cluster to over 10. We've grown from 20 nodes to over 10,000 nodes. We've grown from just a handful of users to over 1,000 users, spanning engineering, data science, business analytics. Most people, when they get to LinkedIn, are interested in finding the data. I think that's one thing that in particular attracts people to join the company. And the first thing that you hear is, well, the data that you're interested in is stored in Hadoop. And in addition to just sort of these raw numbers, I think another thing that is really unique about LinkedIn is the diversity of the people who are using the platform and also the diversity of the use cases that they're seeking to satisfy on the platform. Another unique thing about LinkedIn is that it's always been, at least from a Hadoop standpoint, a very free place. I think a lot of companies or organizations that run Hadoop dictate from above, these are the components you're allowed to use, these are the things you're allowed to do. They try to keep very tight control of it. Due to the way that Hadoop sort of arrived at LinkedIn and the way that it's grown, none of those constraints have ever been in place. People are constantly finding new and shiny things that have popped up in the ecosystem and pulling them in. They're also writing their own frameworks and components. And this ensures, I think, that we're always sort of on the edge of what's new and interesting, but it also creates a lot of entropy and potential technical debt. That's one of the things that I think over the past couple of years we've been focusing on trying to mitigate. So when you hear about Hadoop and you read about it, I think a lot of people tend to focus on scale in terms of machines. But when you start to run Hadoop at scale, you quickly realize that there's an even bigger problem, which is scaling out the people who use it and the processes that they have to interact with in order to get things deployed and running. I'm going to talk about both of these here today and some of the things and work that we've done over the past couple of years to improve both of these problems. I'm going to start by talking about the work we've done to scale out the infrastructure. So if you sort of read blogs or read press releases, go to talks, you'll come away with sort of the conventional wisdom about scaling HDFS, which is that it's not that hard to get it to run, let's say, in a cluster of 4,000 nodes. If you've gone to talks about HDFS federation, you've probably heard people talking about clusters larger than 8,000 nodes. And in truth, it is possible to do this, but our experience has been that it takes somewhat heroic efforts in order to make this happen. Most Apache releases that we've dealt with will not work at this scale out of the box, and vendor distros are not that much better. Why is this the case? Well, one thing I encourage everyone to do is to go and look at the Apache mailing list, the Hadoop mailing list in particular, where you can see how people vote on releases. And you'll see people saying, I ran word count and the PyJob +1 looks good to me. You'll see other people saying, I deployed on a 100-node cluster, everything ran great, let's go for it. And I think part of what's going on here is there's a little bit of a conflict of interest, because for a lot of the people voting on these releases, the release does not represent the endpoint, it actually represents the starting point. That's what they base their vendor distribution on. So the longer they have to wait for an upstream release, the longer their release of their distribution gets pushed out. And from their standpoint, no one's actually using the upstream Apache release. We use it because our experience has shown that even the vendor distributions don't really address the scaling concerns that we have. And similarly, it limits our ability to then backport patches that would be more relevant to the users at LinkedIn. So that brings us to March 2015, which was not a very good month for my team at LinkedIn. This is a chart from Ganglia. You can see that around March, our metric for RPC queue time really went to hell. And it took us about 2 weeks to back this problem out. So what happened? We had a 2,000 node cluster. The ops team had 500 additional nodes that they had racked. We were experiencing capacity constraints, and there was a lot of pressure to bring this additional capacity online quickly. Never do this. We did. I think we knew better, but like I said, there was a lot of pressure to make this stuff available immediately. And within a couple of hours, it was clear that we had made a big mistake. So the latency of RPC requests to the name node shot up dramatically. Jobs started timing out because they couldn't find blocks or talk to the name node. And the really scary thing here is that when you make a mistake like this, it's not really easy to back it out. As soon as you add new nodes to the cluster, blocks start getting written to those nodes. In order to remove them, you'd have to go through a lengthy decommissioning process, which will actually put more pressure on the name node. Another problem is that if you do back it out by removing that hardware, how are you actually going to reproduce the bug in order to get to a point where you can debug it? If this is something that only surfaces when you hit a certain scale. So we basically fixed forward. We spent a week looking closely at the code. We learned a lot about the name node and the process, a lot about its weaknesses. It turned out that the cause of this performance issue was a patch that had gone in an earlier release. It had been present in Hadoop for 2 releases between 2.3 and 2.5. A fix had gone in, but with a very innocuous sounding title. It was also a bug that was present in some vendor distributions that we looked at. The core cause of this is that there's a very sensitive section of the name node code where there's a global read-write lock. And small changes to this code can have very big, and the scary part is somewhat non-linear effects, which you only begin to see the impact of once you get to a certain scale point. So we realized that we needed a better process for doing scale testing. We realized, in effect, that even once we had solved this scaling problem, we couldn't do any more upgrades for fear that in the process of doing an upgrade, we would introduce another scaling bug like this and be right back where we were originally. We looked closely at the way that people were doing scale testing at other companies running Hadoop at comparable scale, and also the way that we had been doing it. And if you talk to folks at Yahoo, eBay, Facebook, places like that, this is sort of the conventional process for doing scale testing. You start by deploying to a 100-node cluster. If things look good, you deploy to a 200-node cluster, rinse and repeat, and pretty soon you have it installed on your largest cluster. Pretty soon, though, is sort of a relative term here. It could take a month, maybe 2 months to do that. In the meantime, you're using your users like crash test dummies, chances are that the smaller clusters that you're doing this on are going to be pretty unstable. So this is a very expensive process, both from the standpoint of the developers that you're paying to do it, the developers who are trying to use this infrastructure and having their time wasted because of instability, and the cost of the hardware that you've dedicated to this process. The other thing about this is it doesn't always really work due to that issue I mentioned earlier of nonlinear regressions. So our solution to this problem is something we call HDFS Dynamometer. Dynamometer, for those of you unfamiliar with the term, is kind of like a treadmill for cars. You can put a car on it. There are big roller wheels that power an electric dynamo. It allows you to figure out the horsepower, torque, and other things like that. For HDFS, Dynamometer is kind of like a treadmill for HDFS. We realized that the critical bottleneck in terms of scaling is the name node. And by isolating that and providing a system that allows us to, in effect, fake an army of data nodes, we're able to trick the name node into thinking that it's talking to 3, 4, 5,000 data nodes when in fact it's only talking to 100. Another interesting thing about Dynamometer is that it's a completely black box test to approaching. We don't make any assumptions about the internals of HDFS. It only interacts with the name node through public APIs, which makes it very easy for us to take a new version in from upstream, get it quickly deployed, and identify any problems with it. The fact that we're able to run it on a fraction of the hardware means that we don't have to dedicate a giant cluster to this process. It also means that we've brought the cost down enough that we can actually run these scale tests in a continuous integration fashion. I promised the people on my team that I wouldn't provide really more details about how we do this because they're working on a blog post which is going to be coming out in a couple of weeks. And I recommend everyone take a look at that when it's available. So on to the next topic, how we have scaled out the people and processes for Hadoop. So if you like dials, Hadoop has a lot of dials for you. And I think this goes back to sort of one of the things I mentioned earlier. As a data scientist or data engineer, when you get to LinkedIn, you're really excited. You're thinking, man, there are petabytes of really interesting data out there for me to look at. But your world up to that point has been R or MATLAB, which is a great environment, right? It's completely integrated. You're incredibly productive using it. And then you find out that the data you want to look at is stored in something called Hadoop, and that it's a huge mess. Maybe a month, 2 months in, you've gotten to a point where you're maybe half as productive as you were using R or MATLAB, and then someone from my team comes in and says, hey, your job is not tuned at all. It is killing other users on the cluster. It's clearly like taking 10 times as long as it should. We need you to go in and tune it. And then you find out that your life is even worse than you had originally suspected. So, what is the root of the problem? Well, typically when new features are introduced in Hadoop or PymK or Hive, they always come with a new dial, a new setting, sometimes multiple such things. And the interaction between these different configuration mechanisms can be hard to predict. Each framework has its own set of configuration parameters. And even when you think you've gotten to a point where performance is good, where the job is properly tuned, just like an older car, you should expect it to fall out of tuning within a couple of weeks in response to changes in the data that it's ingesting or changes to upstream jobs. So this really creates like a constant tax on the productivity of the people trying to use the platform. And in turn, it also creates a tax on the efficiency of the underlying infrastructure. So we address this problem by building something called Dr. Elephant. Dr. Elephant kind of borrows some ideas from medicine. If any of you know like a medical student, you might know that during the first year they actually study lots of flowcharts, these diagnostic criteria for how to distinguish between one disease and another. And we took the same approach with Dr. Elephant. So in effect what this does is it mines the logs from jobs and it uses pluggable heuristics to identify different types of job problems. Users are sort of routed to this web application from links that we embed in Azkaban, which is our workflow manager. And in addition to sort of diagnosing the disease that your job has, Dr. Elephant also offers simple tips on how to treat your job. We found that users do a pretty good job of taking this advice. Compliance with these bits of tips are pretty good, and it has also really streamlined a process both on the user side but also on the operations side where we no longer have to spend nearly as much time sitting down with users and walking them through these steps manually. So we open sourced Dr. Elephant last week. There's a blog post up on the LinkedIn engineering blog. I'd recommend everyone go and take a look at it. I think it's a pretty interesting project. And we're also very interested in collaborating with people at other companies and organizations on this project. We built this to be extensible, and we're hoping to see contributions as well as suggestions from people outside of LinkedIn about how we might push this project forward in the future. So I'm going to take a quick drink of water. Okay, so I talked about upgrading HDFS. I think I established that that's a pretty hard and tricky business when you operate at scale. Upgrading other components on Hadoop, we found, are just as hard, but for a slightly different set of reasons. So when you upgrade HDFS or Yarn or MapReduce, it's very easy to instantaneously kill the performance of everything that's running on the cluster. When you upgrade a component like PymK or Hive, you're not necessarily going to introduce a big performance regression, but due to the exposed surface area of these components, it's very likely that you're going to see at least a couple of jobs break. And from the standpoint of someone who owns a workflow, what they see is my job was running fine yesterday, today it's not running, I didn't change anything, so clearly this is your fault. And in fact, in most cases, the truth of the matter lies somewhere in between. So one of the, I think, long-running problems with the Hadoop ecosystem has been the almost complete lack of class path isolation between different components and layers in the system. And this is a problem that things like servlets, as well as OSGI to some extent, depending on how you feel about OSGI, have tried to address and solved in other pieces of software. But in Hadoop, it's like a major problem. I think that probably one reason why this has been going on for so long is that a lot of the people who work on Hadoop don't actually use it. And as a result, they don't really feel the pain that this issue generates. Probably another issue is that class path isolation, class path pollution, it's easy to think that that's kind of a mundane problem. It's already a solved problem, just not in Hadoop, so it's not going to be that interesting for us to address. And you can also say, actually, this is an issue of hygiene and discipline for users. If they were just better about making sure that they didn't pollute their class path, about introducing transitive dependencies that are satisfied by Hadoop instead of by their own application, it wouldn't be a problem. But from the standpoint of a team like mine at LinkedIn, where this is a problem that really makes us hesitant to do upgrades, it's something that we wanted to address in a more serious way. So one element of of our approach, is to make it easier for people to shade their workflows, to shade the jars that they have in their workflows. So shading is a technique where you basically modify the bytecode in a compiled jar to change the package names. Most people, when they talk about shading, they typically think of it as a way of doing that package name bytecode manipulation and also rolling everything into a self-contained jar. I like to think of shading as like static linking for Java. And some of you may have heard that at Google, one of the rules when you want to deploy your new application or service to their grid, if it's C or C++, you statically link everything. And if you do that, you don't risk falling into shared library hell. So I think the main stumbling block for us in terms of advocating and sort of spreading the word about shading at LinkedIn has been that the tools that exist for shading are not that great. They make it hard to maintain a shaded application as your dependencies change. They're also require like fairly intricate knowledge or deep knowledge of how Java works. If you have any reflection in your code, if you use the service loader APIs, chances are that your shaded application is not going to work. So to sort of make things a little bit better, we've provided what we like to think of as an improved or more intelligent shading plugin for Gradle, which detects many of these issues and helps users to sort of fix them on their own. We've also made it a lot easier to avoid introducing new transitive dependencies that miss your shading filter. Related to shading is another tool that we've built called LightRay, which is a bytecode analysis tool. In effect, what we're able to do with this is audit jar files or zip files when people upload them to our workflow manager and find things that they've included in the jar file which shouldn't be there. I think one particularly interesting aspect of LightRay is that it's actually insensitive to shading. So you can shade a class file, change the package name of it, and we'll still detect that it is in fact the class that we recognized before shading based on a shading insensitive fingerprinting mechanism that we use for class bytecode. Another interesting aspect of LightRay is that in addition to analyzing bytecode, it can also be used to modify bytecode. So when Hadoop 2 was introduced, we had to mount a fairly large migration effort at LinkedIn, getting 1,000 users and multiple thousands of workflows migrated from a Hadoop 1 cluster to a Hadoop 2 cluster. This took over a quarter of effort. And when we looked closely at why this was actually necessary, really the only major reason had to do with the fact that there were a fairly small number of binary incompatibilities which had been introduced between Hadoop 1 and Hadoop 2. And I say binary incompatibilities because Hadoop 2 actually remains source compatible with Hadoop 1. So we had to ask users to go basically take their code and recompile it without changing anything in the source code. And these binary incompatibilities were introduced as a result of things that had been classes in Hadoop 1 getting changed to interfaces. So it's kind of weird, right? That your source code doesn't need to change. Your dependencies only change slightly, but your code won't run unless you go and recompile it. So LightRay is something that we modified to actually go and fix the bytecode in these Hadoop 1 projects so that it would work with Hadoop 2. This ended up saving a lot of time during the Hadoop 2 migration. I think it's kind of an interesting example of a change that you make in one place in order to save a bunch of people at your company a lot of wasted time making the change elsewhere. This is a quick example of LightRay in action in Azkaban, where it's basically looking through the binary artifact that a user has tried to upload, found a prohibited jar file, and is telling the user that they have to try again after removing that code. Another project that we've built is something called Soak Cycle. So I mentioned earlier that upgrades are hard. One of the things that makes them hard is there's a lot of exposed surface area. You look at something like Hive, Hive has literally thousands of tests that come bundled with it, tests which involve a little SQL script that's run against some sample data. The output that's generated is then diffed against the expected results. And even with these thousands of tests, every time a new release comes out, there are still performance regressions as well as simple like correctness and bugs that are introduced with it. And that's really a result of the fact that when you talk about something like SQL or PIG Latin, there are literally an infinite number of ways that you can combine the different operators in that language. So getting complete testing is really impossible. If you look at what some of the vendors have done, they try to improve on this a little bit by writing some of their own tests. But having worked at a vendor, I can tell you that that's kind of a losing battle, right? People are always going to introduce features at a more rapid rate that you can add tests for them. And you can never really anticipate the ways that people are going to actually use a flexible system like that in practice. I think one of the interesting observations about a place like LinkedIn, as well as other companies of its size where people use these components, is that you literally have a population of people who are writing integration tests for you every day and updating those integration tests. What I'm talking about is the actual jobs that people are running on the cluster. And this gives you perfect fidelity, right, between what you're testing and what you actually need to test. The only problem is figuring out a way to take these existing flows, queries, scripts, and use them as test cases. So what we've done with Soak Cycle is to basically create a sandboxed cluster where we have a sample of the data that we have on our real clusters, and we deploy a test version of Hadoop, or a test version of Hive or Pig or Spark to one of these clusters. And then we forklift jobs that we've observed to run on our real cluster and pass over to the Soak Cycle cluster en masse and run these jobs. And we expect some of them to fail, in some cases because all of the data they're looking for is not there. But generally, just by having, let's say, 10 days of tracking data available, most jobs will tend to succeed. And using some simple heuristics related to ratios between the expected size of input data and the actual data that they see on the Soak Cycle cluster, we're able to catch performance regressions. We're also able to catch more obvious errors like a job succeeded before the upgrade and post-upgrade on Soak Cycle, it's failing the class not found exception or something like that. So this is basically a shotgun approach to testing, but it's a great way of getting a quick signal about whether an upgrade that you're planning to do is going to break a lot of stuff, and it also gives us a way of warning users in advance that in cases where, let's say, someone's depending on a private API that they shouldn't be, these folks can get warned that once we do the upgrade, their flow will break, and they need to address the issue before that. So in terms of the future, I think there's quite a bit going on lately. One big thing, I think, or I would say more of a general theme throughout the Hadoop ecosystem, and I think something that's really been happening since 2009 when I got involved in Hadoop, is that we've been incrementally moving in the direction of making Hadoop look more and more like a database. In the good ways, not the bad ways. And over the last year or two, I think one big thing that's come out is an increased interest in fine-grained security. At a place like LinkedIn, that's going to be a real game changer. We have a lot of data right now which can only live in Teradata or Oracle because that's where column-level access controls are available. It used to be that if you wanted column-level security in Hadoop, your only real option was something like Hive Server 2. Now we see components like LLAP in the Hive project and record service. I think it's interesting that when these components were first put together, I think the people building them actually underestimated what a big draw column-level security would be. I think they thought of it more as a way of, well, we're going to take a structured API and move it from the client side over to the data node side, and there are some performance benefits that come with that. But when I've talked to them since then, they say, well, in fact, customers are excited about this because it gives us a way of enforcing fine-grained ACLs. I think another thing that's happening is that we're seeing more of an interest in higher level abstractions for accessing data in Hadoop, which goes back to things like record service and LLAP. This distinction between saying I want a logical view of my data and I don't want to worry about the physical details, things like storage format. I don't want to have to embed the schema of the data that I'm looking at the beginning of every MapReduce job or pig script that I write. And the eventual direction really of saying, I don't even want to worry about where this data lives. I want to have what is in effect one big file system or one big data set storage system and give people managing the infrastructure more freedom in terms of optimizations they can do behind the scenes about data placement, about pre-positioning data in nearby clusters and things like that. So I like to think that this idea, this set of ideas really caught on in 2015. You had things like data frames in Spark, which are more or less just tables by another name. You had projects like HCatalog, which came out somewhat before that, where the core idea really is taking these nice abstractions that started in the world of databases and then migrated into Hive and making them available to every other component in the platform. And in 2016, I like to think that we're going to make this kind of the year of the view. So we have a project that we've been working on for a while now called Dolly, which is a logical data access layer and abstraction on top of Hadoop. It's kind of similar to things like HCatalog, but I think one big change that we've made is, in addition to tables, we're now also making views accessible to the other components in the system. And when you start using views, there are a variety of really interesting optimizations that you can do behind the scenes that otherwise are not possible. And you can start to think of your whole data flow pipeline as one big hierarchy or nested graph of views, which opens up some other interesting possibilities. So I'm giving a talk on this tomorrow. I'd encourage everyone to attend if this sounds interesting. And with that, that's the end of the talk. Are there any questions? Yep. Well, magic, perhaps? I don't know the answer, I'm afraid. I mean, one of the things is LinkedIn is a big place at this point. I know people who work on the PymK team, but I don't know the answer to that. And in some ways, I'm not even sure everyone on the PymK team would know. PymK is a monster workflow at this point. And it started out simple. I mean, I think I talked about how it's just fundamentally triangle closing, but at this point, there's a lot more to it than just that. So my understanding of it is very primitive and I think fairly antiquated. And though I was able to sort of give you the basic idea of it, I can't do justice to it. But I think you can find my email address. Feel free to shoot me an email and I'll try to figure that out for you. Yes?
So you talked about RPC calls, right? And what if like someone writes an like a job which creates like 20 million RPC calls? Like I know like Dr. Elephant can identify it, but can you stop the user from rerunning the same job again?
So actually, RPC calls to the name node, for example, is not one of the things that Dr. Elephant can currently recognize. I think one technique is to basically tail the name node audit log. And that's one of the things that we do to sort of get some real-time monitoring of the load on the name node. And this kind of also relates to one of the other sort of like ongoing and bigger problems with the core Hadoop platform, which is it's really easy to DDoS different elements of the system. And when you start to think about it, I mean, like Hadoop is in effect like, it's like a platform that allows people easily to write applications that DDoS different components of it. So I think one thing that we're working on is basically the ability to throttle HDFS clients from the client side. Another thing that I probably should have mentioned earlier is that when we were investigating our March 2015 nightmare, one thing that we quickly realized is that the metrics that are available for the name node through JMX only give you a very small piece of the picture. I mean, one thing that's, I guess, kind of obvious is that these are metrics that are collected on the server side, so they give you a hint about the sort of quality of service that clients are seeing, but they definitely don't tell you the whole picture. Similarly, like, the metrics are very coarse-grained. they tend to lump different RPC types together. They don't give you a good idea of the relative costs of different RPCs. And I think these are all areas that could be improved quite a bit. Any other questions? Yes?
Do you see a future Hadoop replacing classical relational databases?
How to replace relational databases?
Yeah,
for online. So I think that sort of transactional approaches, things like HBase or systems built on HBase seem to be the best thing that people have come up with so far. To be totally honest, like OLTP stuff is not really my area, so I'll just say that it seems like a very hard problem and one that fundamentally you sort of run into some consistency and scaling problems there. I guess we'll see over the next couple of years. Any other questions? I don't see anyone, so, oh, yes, in the back. It's possible to do that. For the time being, we're building Dolly largely on top of Hive. And I want to stress that that's kind of, I viewed as a temporary implementation detail, something that we're quite likely to replace in the future with maybe one of the other SQL on Hadoop components, or maybe not, depending on how Hive fares over the next couple of years. I say this because SQL on Hadoop has become a very crowded market over the last couple of years. And I think one thing that we decided at the beginning of the Dolly project was that it was you'd sort of be foolish to bet on any one of these components. The only, I think, safe bet is SQL. So we've tried to only sort of be tied to that. Hive, though, has a lot of interesting extension interfaces. And one of those interfaces is something called a storage handler. So you have something that looks like a table, but instead of pulling its data from HDFS, it could pull its data from any other system. So there's an HBase storage handler, there's a storage handler for Cassandra, and other things like that. And this is an idea that you also find in other database systems. Postgres has something called foreign data wrappers. There's a really cool project called Multicorn that allows you to write a Postgres foreign data wrapper in just a couple lines of Python. Apache Derby has something called table functions. And this goes back to the idea I mentioned earlier of let's make everything look like a table. It's a really nice abstraction. Once you have that, you're able to leverage the power of your SQL engine on top of it. So, going back to your original question, yeah, I think that is something that we're quite excited about, being able to leverage storage handlers to union across both HDFS data as well as data pulled from other sources, and then also in the future, maybe potentially switching to something other than Hive if need be, and being able to leverage a similar abstraction there. Another question?
It sounds a little bit like Drill.
I think Drill does many of those same things. Yep. Another question?
Do you guys have preemption enabled on the cluster? If not, how do you guarantee SLA for thousands of users?
Right. So right now we don't have preemption enabled. It's, in a sense, impossible really without it to guarantee SLAs. But one way that we help to improve the situation is by providing org-level queues. And we've invested time over the past year in providing a mechanism that allows people basically to own a queue. And a queue is a way of sort of partitioning compute capacity on top of a shared storage system. And whereas that used to be sort of an admin-only option, the functionality that we've added internally gives, let's say, managers or department heads the ability to own a slice of this capacity and then actually sub-partition and divide that capacity among the teams that report to them. And while it doesn't really solve the problem, it does help to sort of contain it. Another thing about this is that when you have, let's say, 1,000 people using the same cluster, there's very little incentive for one person to try to be efficient because you're in a situation where really one person can't make a difference. By providing these org-level queues, I like to think that we've kind of enabled some vigilante justice. It's a lot easier now to go and find the person who's hogging all of the containers because they probably sit next to you. And while I don't think that's like an elegant technical solution, it's, I think, an elegant social situation to a problem. Any other questions? In the front?
You highlighted HDFS as having performance would you think would cause performance issues, like if you talk about Spark, Hadoop? Are there any common performance problems that you hit?
I think we've seen stability issues with Spark, and that's one of the reasons why, for the time being, our sort of advice that we give to other teams at LinkedIn is that they should only be using it for iterative machine learning tasks. I think one thing that Spark got really right, and I think in a way sort of they had the benefit of looking at what was wrong with MapReduce and fixing it, is they realized that APIs really matter. The APIs in MapReduce were written by, I think, a group of masochists, because they're pretty gnarly. They make it really easy to write broken code, hard to maintain code. And Spark, by comparison, has a really clean API. It's an elegant API. And I think that's one of the things that's sort of, in large part, making that platform as popular as it is. I'm hoping that over time they start to address some of the stability and scaling issues with Spark. I think another issue, which is just kind of inherent to Scala, is that when things fail, you get incomprehensible stack traces. Although, I think the more you learn about Scala, probably the more comprehensible those things become. But in terms of, let's say, hard distributed systems problems, I think probably HDFS, the Spark scheduler, things like that is really where the action is these days. Any other questions? Yep.
My question is, how fragmented are your data? Are in different systems, different formats? How fragmented are they?
So I think LinkedIn's data infrastructure is largely split into two halves. There's the online side and the offline side. So the online side is member-serving systems. The offline side, for the most part, is Hadoop. There are a variety of different paths that data traverses, moving from the online side to the offline side and then back into the online side. There's some good presentations you can find online about a framework we've built called Goblin, which is a unified ingest framework for Hadoop. I recommend taking a look at that. It's also open source if you want to look at the code or try it out. But yeah, I think it's, I didn't have time to show it, but I have a great diagram that I can point you towards, which sort of shows the lay of the land. I think I've run out of time, but feel free to come up and chat with me afterwards. Thank you.